Meme review. Over the years, I've both made and compiled a large number of physics memes, or I guess more specifically related to high energy theory, which a lot of these are, like particle physics and gravity and whatnot, but also just physics in general and kind of the experience as a grad student or an undergrad student. Um, and and so I thought it would be fun to go through these, explain them, and in the process put them on a tier list, see how they rank. All right, so I guess we can begin with it's this one. Say, Flag of Norway if it was a non-abelian gauge theory, followed by the city of St. Louis. Okay, so you look at the city of St. Louis, at least the first thing that comes to mind is that it looks like the flag of Norway, which is the similar kind of construction, except it's not straight, not wavy, and there are four, it's like a cross, not these three things. But kind of as someone who studies high energy theory, this looks a lot like these Feynman diagrams associated with Yang-Mills theories, these non-abelian gauge theories. So usually Feynman diagrams encode how fields interact. So for instance, if I have an electron, a positron, this can interact through like with the photon field. So this is an excitation of the electron or positron field, and then at some point you excite the photon field, and the way this happens is by creating a photon. Sometimes this photon is not like really real; it can be like a virtual photon. But for instance, you could have two electrons scatter. So this is like, you can think of these classically as like two billiard balls, but the scattering process is quantum. So two electrons come in. These are two kind of waves, excitations of the field, and then each of so they interact with the photon field, and through this you have this mediation. A virtual photon is transfers momentum from one excitation to the other, and so after this, the apologize for my writing. I'm using a mouse. Electron excitations, like they scatter off each other, they emerge with different momenta, and so these are Feynman diagrams, and photons or like gauge bosons, these force mediators, they're usually depicted with these curly lines. But at least in quantum electrodynamics, this thing can't interact with itself. So for instance, you don't have like this 3-point vertex or higher point vertices. Well, this is no longer true in these non-abelian gauge theories. For instance, the prototypical example of this is in quantum chromodynamics, which is a theory of gluons in like gluons and quarks. They mediate the strong force, and so this kind of stands out because um, you can have a vertex that corresponds to three of these field excitations interacting with each other. Um, and these are sort of kind of complicated to draw, I guess. People don't like drawing these. Sometimes they're like, people use this kind of springy notation, but each of these is a gluon. And so, the field can like interact, the excitations of the field can interact with itself. And so so for instance, if you draw like gluon 3-point function, then you'll see that it's something like this or like this. They're not always drawn like the loops. They're just generally like wavy, I guess. And so right, so you can use this to explain lots of hadronic processes that happen at the LHC, and the observation was that just this looks a lot like the city of St. Louis flag in the theme of Norway. Oh, actually, there's one more caveat you can say. This circle, I mean, often in QED. So like, you have to correct a vertex. What does this mean? Well, like you have to modify it a little because of some reason. So people can put whatever in here. For instance, they can put an X here. They could put like a letter here, and this just tells you that this vertex has been modified. You have to do this you have to do this through normalization, because if you don't modify then the vertex, then it can pick up like higher corrections that can cause it to diverge if you don't treat them well. So you can hide like a bunch of uh, physics in here that make your theory more well defined. So this sometimes goes by like renormalization group improved perturbation theory. The point working with Feynman diagrams is you're doing perturbation theory basically because it assumes that the amount of the diagrams with fewer interactions, with fewer, I guess, vertices dominate, which is good when your interaction is weak. Your theory is almost free. So this is kind of like this is perturbation theory. So like if this kind of fleur de lis in the circle that's centered on the vertex, this looks like a counter term, like a French counter term basically. So that's kind of why I made this. I mean, it's kind of dumb, but I think I like it. Let's see. Maybe I'll put it. I'll give it a B tier. Okay. Next one. Little known fact: the stop in stop quark is stop squark rather is short for sloppy toppy. Okay, so this template I was working on, like the who needs they a 8 meme, like these things, that was popular for a while. Okay, how to explain this? So some background. This H stands for the Higgs field, and so here this is another Feynman diagram of the Higgs field interacting with a quark field. This is the top quark. The top quark is the heaviest quark in the standard model, and basically each heaviest particle in the standard model with a whopping 173 giga electron volts. And so, a quark, a top quark, is an excitation of the top quark field, as is the case with all of kind of quantum field theory. Particles are excitations of fields, and so the Higgs interacts with the top quark field through this kind of loop correction. But this loop correction actually changes the Higgs mass is sensitive to these corrections, and in particular it's dependent on things like the top quark mass. So if there are even heavier particles in the standard model that we haven't discovered yet, maybe something between electroweak physics and like say Planck physics, that would change the Higgs mass. And so naively, you'd think that the Higgs mass, because this is sensitive to Planck scale physics, for instance, if there's like a super heavy right-handed neutrino, or basically anything in between, which, I mean, probably exists. I mean, I think it's quite, it would be super interesting if there was nothing between new particles between electroweak physics and like grand unified or Planck scale physics. But that would sort of, you would naively think that the Higgs mass, which comes to 125 GeV, I think, should actually be order Planck scale, because it's enhanced by these corrections, or it's sensitive to these corrections. And the Planck scale physics is like 18 or 15 orders of magnitude greater than the Higgs mass. So like, why is it so small? This has a name for it. It goes by the hierarchy problem. And this is a big problem that people care about in the field. It's unresolved. There are many solutions that people have like postulated, basically through just like building different kinds of models that could solve this. One of these models is supersymmetry. So the idea for supersymmetry is that for each field or each kind of particle, there exists a superpartner. So there exists another field with the opposite spin. Sorry, not opposite. With like, if a field is bosonic, if it is integer spin, then the superfield, the superpartner, has half integer spin, and vice versa. So the opposite of a top quark. So you often put s's at the front of these, at the front of fermions. So like a lepton is the superpartner is a slepton, and a quark is a squark. So a top quark, the superpartner would be a stop squark, which is represented by this diagram, and this is a spin. This is a spin 0 field that is supposedly much heavier than the top quark. And because this is opposite spin, if you compute the correction of this to this the Higgs mass, it actually exactly cancels out with it cancels out with the top quark contribution. So this is very nice because if this happens for each superpartner, so then if supersymmetry is true, then there's no kind of reason that the Higgs mass would be sensitive to all these high energy Planck scale physics, and the hierarchy problem is basically solved without fine tuning, I guess. So I guess, yeah, before, if there's no supersymmetry, there's this notion that the Higgs, all of the corrections to from heavier particles, from top quark mass particles all the way to Planck mass particles, they have to be super finely tuned so that the Higgs mass is like very small. For instance, if you take like some numbers that are order a million, right? If they're like generically 6 of these, the fine tuning would be like you have all of these, the sum of all of these things is very small. So maybe like you have a million, you have 2 million, you have minus 3 million and whatever, but all of these, the sum of all of these numbers is order, say, like 1 rather than a million. So this is called like fine tuning, and basically the particles would have to be super fine tuned in order for the Higgs mass to be small if in the absence of supersymmetry. So with supersymmetry, this is no longer true. The Higgs mass is naturally small, so there's this like naturalness notion versus this sort of fine-tuned notion. And yeah, by like basically, if you complement each of the superpartner contribution with the usual contribution, then they vanish, and so the Higgs mass can be it's naturally small. It's naturally like in the 100 GeV range. So I guess I cast this. Well, I don't think I made this actually. I think I found this in some Facebook group. But yeah, this is like a long time ago. So apologies if I can't remember the source. Right. I kind of just put well, not me, sorry. The creator put this put this kind of no idea in the spirit of the who need they blank 8 meme. Oh, there's also that SUSY ends in the USY prefix, I guess. That's pretty dumb, but I think that's probably like the thing that prompted the meme from being created. So I quite like this. I think I would give it A tier. Okay, let's go on. Oh, there's one I think that's kind of related to this. There we go. Okay, so let's expand this. So my friend made this meme: average naturalness fan versus average fine-tuning enjoyer. And so, okay, this is supposed to be kind of like facetious, but so yeah, related to the Higgs is one the hierarchy problem in the Higgs in Higgs physics. It's one example of where you have this fine-tuning problem, where it seems that like you have something that is small but you shouldn't expect it to be small because you can get it from this big calculation that involves, say, large numbers. And so it's like adding 5 numbers that are large. You should expect that it remains large instead of canceling out to give you something very small. So whenever that happens, your theory is called fine-tuned, and that's a problem because you shouldn't expect this to happen generically. It's sort of like, yeah, it tells you often that maybe the model is problematic or you're missing some physics. Maybe there's some symmetry that accounts for that enforces the sum of these big numbers to be small. So in general, fine-tuning is bad. People don't like it. People actually mauled really hard if there's a fine-tuning problem. Instead, they prefer, for instance, if there's some symmetry that gets rid of the fine-tuning and makes kind of masses like naturally small. This is called naturalness. And so a lot of the time you have people in the field that are like, naturalness is I mean, it's in the name, right? It's natural. This is what you want. And so they they try to come up with all of these bizarre, well, seemingly bizarre models or mechanisms that explain why something is natural. So it's kind of like a lot of cope, I guess. Maybe some people might think it's basically doing a lot of heavy-handed work to try and see to hopefully show that there is some mechanism accounting for this seemingly fine-tuning. And that's that they're depicted in the first frame, kind of like mauling and mad and, waving their hands, trying to justify whatever. I guess on the other hand, you can just accept that something is fine-tuned and like just stop thinking about it. Which is, I mean, it is a problem, but it's not a problem if you just ignore it. I guess so. I don't know. I think, like, in the process of explaining these, it's I don't know if they're funny, but that's sort of the punchline. The punchline is, instead of like writing papers and spending like years of your life trying to come up with reasons that remove fine-tuning, you can just accept it, not think about it, and worry about other problems. And so you're depicted as this Giga Chat over here. This is kind of a low effort meme, I think. So I will put it here. Okay, what about this one? So they're looking at a table, and the table you can open the table up, and there's some like part in the middle that it extends. So the guy's going, yes, it's an extender. Okay, this is sort of, I mean, it's not that niche, but here what they're looking at is the Witt algebra. So the Witt algebra is it's an infinite dimensional Lie algebra. So here m and n, these are indices that are integer. They can go from -infinity all the way to +infinity integers. And so you have like L0, you have L1, you have L-1, and all the way. So you can think of these as like, you can kind of think of them as infinite dimensional matrices if you'd like. More generally, they're just members of what's called the Lie algebra, which is the tangent space of a Lie group, which is a manifold that also has some group-like structure. And the kind of important thing you can do with Lie algebras is that you can take, so products aren't necessarily defined, so they are with matrices, but Lie algebras are more general than matrices. So products aren't defined, but what you can define are commutators. And commutators are basically you can take two members of the Lie algebra and get a linear combination of other elements. So here you can see that you're taking the commutator between Lm and Ln, this is equal to a third element that is given by m plus n. So let's see, how do I So this is called the Witt algebra. It makes appearances in string theory, and basically this is it's a classical algebra because it's a classical Lie algebra because um, you have some elements, you can take their commutators, and there's this rule that tells you that when you take two commutators, it spits out sublinear combination of elements of the original Lie algebra. And one manifestation of the Witt algebra, I think you should think of Ln greater than 0, I think, as like multiplication by z to the n. So z is like some polynomial, and so what this thing is doing is you're multiplying whatever function by z to the n, and if it's less than 0, you can think of these as sort of differentiating n m times. So like, I mean, there's some coefficients here, but like that's kind of one way of implementing this algebra through differential operators. Right. So the thing is, if you take like a string theory course, then you don't actually deal with this guy. You deal with this guy. So if you look at this thing, this new kind of these new commutation relations, they differ by this new term, and C is a constant. C is called the central charge, say of like a conformal field theory. M is this M, and here you have if m equals negative n, then you get this new kind of factor. So this is called a central extension. It basically means that the central extension of a Lie algebra, I think there's some uniqueness theorem, but in addition to the to the original algebra you impose, there can be some constant that you get, depending on the values of m and n. And so this is called the Virasoro algebra. The Virasoro algebra is the central extension of the Witt algebra. So this is a classical object, but when you look at what happens in quantum theories, then often you have these central extensions of your classical algebras. And how can you think about the Virasoro algebra in the context of string theory? Well, in string theory, there is a stress energy tensor. There's a stress energy tensor that encodes kind of the energy momentum of your theory, and so it's a 2x2 matrix. It has two non-vanishing components. I'll call them t and t bar. So this is a function of z, which is a two-dimensional. Okay, so in string theory, you have kind of strings that can merge. Okay, and so as you basically, a string moves through time, it can split off, or it can merge into more strings. And so the kind of the surface traced out by the strings is called a world sheet. It's two-dimensional, and they're actually called Riemann surfaces, which are these kind of two-dimensional nice manifolds that are also holomorphic, which is a nice structure that becomes very useful. And so this z encodes basically the coordinate along the world sheet. So it's two-dimensional, so z has two components. So there's a holomorphic, there are two components of the stress energy tensor, one that's holomorphic and one that's anti-holomorphic, or analytic, I guess. It basically means complex differentiable. But what you can, so in the quantum theory, these become operators, and actually what you can do is you can consider moments of the stress energy tensor. So I can define this as Ln. And I can do similar with like L bar n equals like moments of the stress energy tensor. So you have L's and L bars, so you have two sets actually of the Virasoro algebra that don't talk to each other, but we can just look at the first one. So these are moments in the same way that like if you have a moment of a probability distribution, then you just like, you know, multiply by something. And I think you have to integrate this along some how to say, initial value surface. But if you consider these operators, these quantum operators, you can take their commutators, and they generate these objects. They generate the Virasoro algebra. So the stress energy tensor, it tells you about the energy momentum, I guess, of your theory, but more generally, it tells you that it's related to this thing called a diffeomorphism in invariance, which basically encodes that my theory should not depend on a change of coordinates. If I change my coordinates, and then like the theory should remain the same. And then there are different ways that I can change my coordinates, and then the ways I can change my coordinates correspond to moments of the stress energy tensor, I guess. And so this algebra, it encodes the diffeomorphism invariant structure of string theory, sort of, kind of. And yeah, you can do this either classically, in which you pick up the Witt algebra, or you can upgrade it to a quantum theory, and you get this extension. You get the central extension. C here is something called the central charge. It encodes the number of low energy degrees of freedom of your theory. Right. So that's what this means. It's kind of complicated, but you have this Witt algebra, and they open it up. They're excited that there's this extension. This extension actually gives you a lot of really cool physics in string theory. So this C, the value of this C is associated to something called the conformal anomaly, and basically you want that to vanish, which enforces, which tells you that string theory only makes sense, at least bosonic string theory, where you have where the strings are they're spin zero, sort of. The bosonic string theory, that tells you why bosonic string theory only makes sense in 26 dimensions. You need this conformal anomaly to vanish. But yeah, they're excited about that. This is an extension. So this is kind of low effort, but I mean, I quite like it, but I don't know. Let's just put it in C tier for now. Okay, continuing with the string theory. Memes. Okay. Jesus. So this is even more, maybe. Well, let's see. So what's going on here? She rolled down his D brain till it condensed. Okay. How to explain? So this meme is about string field theory, and string field theory is what happens when you try to encode string theory as a quantum field theory. So to do this, you need actually an infinite number of quantum fields, and so an infinite number of fields, they all kind of interact in a way, and you expect to recover string theory. So why is this useful? Why do people do this? One of the traditional ways that people talk about string theory is perturbative string theory. So the idea in perturbative string theory is that, so you fix your background. For instance, you're working in a 26-dimensional vacuum. I mean, here I'm drawing 3 dimensions, but pretend it's 26. And about this vacuum, you kind of study strings that like can sort of split, I guess, and merge and join together. And this is the world sheet that I talked about. So you have these strings, right, that over time they split. So I could draw this like a time-like direction. And you can have like different, you can have another kind of string doing its own thing over here. So maybe this one might split, and these could be disjoint. But this is, so basically these strings, okay, so if you have a string, and if this string is kind of wiggling, like you might imagine, over time, this is wiggling in the transverse directions, then this gives rise to a particle, actually, because if you zoom out on this far enough, a cylinder just looks like a line, so this just looks like a particle going through time, but yeah, these wiggles correspond to like modes of the string, and different wiggles, different harmonics will give you different particles. So you might get like a graviton or a photon or whatever. But I guess the important thing is that you have all of these, you consider free strings about a vacuum. So like the vacuum is boring, and yeah, you consider the dynamics of strings just about them. So for instance, if I have 2 strings that come from past infinity, and what they can do is they can scatter. So over time, like they might interact, right? They might interact, and then they might so they'll interact, exchange momentum, and 2 strings will fall out. And there can be more complicated interactions. So for instance, this diagram could be like, there could be a hole in here, this could be a torus. This is called the 4-point torus amplitude about flat space. And yeah, this explains how strings scatter, how strings interact perturbatively. But this is kind of problematic because, well, for 2 reasons. I guess one reason is that there are other, you might want to consider strings about other backgrounds. So for instance, if there are enough strings kind of floating around, they can actually form some kind of like condensed, some kind of phase transition. And because strings consider the strings, they have energy, right, associated with them. They have energy and momentum. If there are enough of them, then that will actually cause the background space to curve, and it will let the background field be very non-trivial. So for instance, this might cause the background to be like ADS space-time, or some just like super weird space in which this approximation is no longer true. I can no longer think about free fields interacting about some kind of background. So I guess what happens is that you can have some kind of how to say, well, I won't explain this axis for now, but you can have sort of like, well, yeah, maybe I will explain. This corresponds to some background expectation of some field. So T denotes, well, you can just pretend this axis denote like the background value of the space-time, some space-time, well, for instance, if I have like a field in, I could let this denote its background value, and basically you could this point where this has zero background value. This corresponds to the Minkowski vacuum, which is the vacuum I was talking about, the boring vacuum where there's nothing, and you just take strings kind of propagating. So basically, that's you looking at this point, and you quantize the theory about this point. So like in the beginning you think of strings as classical objects, but then you can promote them to quantum objects. But the problem is that when you do so, you're only working about this vacuum. You don't consider processes. This cannot be generalized to processes where the background space-time looks something different. And so when this is called perturbative string theory, but the problem is that the perturbation series has zero radius of convergence. So whatever you're doing, you're only doing at this point. And say if the background field takes on another value, if the space-time say looks something different, then you don't know anything about it. And the field, the space of background values of fields in string theory, this is actually incredible. It's enormous. And so if you stick to doing perturbative string theory about these like fixed backgrounds that you don't get very far. These are only like lamp posts that have like zero radius of illumination. This doesn't tell you anything about what happens in between. So another question is, why might you want to concern yourself about what happens in between? So there are different answers for this. One answer comes from doing the quantization, and this is what you do in like a intro to string theory class. You study the bosonic string about the 26-dimensional Minkowski vacuum. But then something very problematic occurs when you quantize this. And one problem is that you see a tachyon. So a tachyon is something with negative mass. It's an excitation with negative mass. So it would move backwards in time. And so this tells you that your theory is something's not quite right. This is not too bad though. It's not like the end of the world. In fact, the reason why you generally see these tachyons is because you're expanding around the wrong vacuum. So, for instance, I could do the same with the Higgs potential. So, in the standard model, you have a Higgs field, and this Higgs field has two components, and you could consider quantizing the Higgs field about a specific background. And people generally, the kind of naive thing to do is you do it here, but if you do it here, then you find a tachyon. And so this is kind of the wrong vacuum to expand around. So what is this axis? This axis is something called the Higgs potential. And the potential looks something like this. So it has this Mexican hat shape. This is like... So actually it has a local maximum at 0, but the value where it takes its minimum is actually like, it's here, it's along this kind of surface. That's probably not very clear. But so you actually want to quantize the theory about this vacuum, the vacuum where the Higgs expectation, the background expectation of the Higgs field is non-zero. And if you do this, then you don't have any problems. You the tachyon sort of disappears. So this is the potential associated with the Higgs field, and if you expand around a maximum or something that's not a minimum, then you will find a tachyon. But this just tells you that you're expanding around the wrong theory, because if you have any sort of excitation here, then this will kind of like cause some kind of vacuum decay, and it'll cause you to tunnel down to the true vacuum. So you have a false vacuum and you have a true vacuum. And the similar thing is true with string theory. So you have so you have this kind of false vacuum where if you expand around you have a tachyon, but then so you have a potential, and this potential is a function of the background value of one of the string fields. Remember, we're working in string field theory, where you want to formulate the degrees of freedom as fields, and so one of the fields is called this tachyon field. And here, if you expand around this potential, then you have this tachyon. But this tells you that you're expanding around the wrong vacuum. String theory allows you to get some traction on this true vacuum. And if you expand around this proper vacuum, then there are no more tachyons. There are no more particles that have negative mass. I guess you might ask what happens over here. I don't know. I don't think people really know. Maybe there's some what the landscape looks like. But I guess the moral is that if you just do naive string theory that you do in like a first or second course in string theory, you do perturbative string theory, you can only know what occurs in an infinitesimal neighborhood of this point, and the background value of this field cannot change. But string field theory, it allows you to get some traction on what this point looks like. So this is called this is the perturbative vacuum. This is the closed string vacuum, and so this is you, because you're a small brain, and you can't you're working around this kind of sick vacuum. This is the value of the string field. It tells you everything about sort of the dynamics of what happens here, and this is the sort of the field, the vacuum that you should be expanding around, that string field theory makes tractable. And something really incredible happens at this point. So let me explain. So in string theory, you have open strings and closed strings. So there are two kinds of strings. One kind of strings are one-dimensional objects, and so they're closed. They kind of wrap around themselves, and this thing can propagate through time like so. But you can also have an open string that looks like this, and the endpoints are distinct. So as this goes through time, it'll look like this. And so you have these kind of endpoints, and there's this idea that the endpoints of open strings must lie on what's called these branes. So you can think of D-branes, they're called Dirichlet branes, as these membrane-like structures on which the endpoints of strings must end. So for instance, I could have this kind of membrane structure, and I could have another one here. These are really like dynamical objects. So I could have a string with one endpoint on here and another endpoint on here. And basically the idea is that as the string kind of evolves, the endpoints must stay on these branes. Of course, the branes can also move in time. So in bosonic string theory, so these are called open strings and these are called closed strings. So these D-branes, you can really think of these as membranes that have their own energy and have their own dynamics. In open string theory, when people first started doing string theory, they didn't know anything about these D-branes, so they just thought of open strings kind of moving through space and time in 26 dimensions. But it turns out that if you consider this theory, it's basically where the endpoints of the strings are not confined, they can just move freely. That's the same thing as considering a theory where the entire brain just fills the space. So because the brain fills the space, it's a D25 brain. So you have 25 spatial dimensions and you have one time dimension. So the brain fills the entire space and it moves through time. So it's called a D25 brain. 25 is the number of dimensions. And because the restriction is that the string endpoints must stay on the brain, this is fundamentally what's happening when you study open string field theory in 26 dimensions. You're really implicitly assuming that there's a brain, and this is the perturbative vacuum. But if you use closed string theory, if you use string field theory to study this vacuum, this true vacuum, the point at which the tachyon potential is minimized, then what happens is the D25 brain is no more. The brain sort of vanishes, and because the brain vanishes, the brain sort of condenses into what it's kind of mysterious. There are no more open strings because open string endpoints must end on D brains, right? But if the D brain is gone, then that means that open strings have no more. The endpoints can't be anywhere, so there can not be any open strings. So because there are no open strings, there are only closed strings. So this is called the closed string vacuum, and you can actually compute the difference in the potential, the kind of energy between this point and this point, and this is actually exactly equal. This is sort of amazing to the tension in the brain that's at this point. So this really is evidence that shows that the brain has vanished. It's condensed, and what you have here is this mysterious, super mysterious vacuum involving no open strings and only closed strings. And do I want to explain what this formula is? Okay, so this is called a string field, and this contains the information about. So again, in string field theory, you want to you want to cast string theory as a field theory, but you need an infinite number of fields, and this field contains, it's really an infinite number of fields, and you can build these from these individual objects that TBH I don't even remember. This is actually a closed form expression of this what happens at this point. It's amazing that this exists. This is called the Schnabel solution. It came out, I think, in 2006. So what's the meme? The meme is she rolled down his D brain until it condensed, because you start here, and then if you want to look at the true vacuum, which minimizes the potential, it's like a ball rolling down a hill, then it does so, and in rolling down the brain condenses. So of course this is one of those. The template is like she blank his blank until it blank, where you can fill these in however you want. And so this is right. You can't do anything here. This is the naive thing to consider. And here's where all the true physics lies. So this is no radius of convergence. It's making fun of the how you can't do anything here. How it's kind of weak. Right. Okay. So that took a very long time to explain. But let's put this. This is maybe a B tier meme. Yeah. Okay. There's this meme, which is I mean, this is a play on the Mark Zuckerberg Markiplier um, meme, right? Where it's just E. Um, it's one of these deep fried memes where like it's a picture. What's it? You start with a picture of Lord Farquaad, and then you put Mark Zuckerberg's face over it because I guess he's also robotic, and you know, his like it's bad CGI, looks like not CGI, it's bad animation, looks like Farquaad. Also, Farquaad is a piece of shit, and so is Zuck. This is a picture of him in Congress, right, like talking about Facebook election fraud, whatever, and then people are like, Mark Zuckerberg slash Farquaad looks like Markiplier, you know, the gamer. So they put this face on and they deep fried it, so it's like many layers of irony, and they put E. Um, but instead of E, it's it's psi. I can't explain this meme. Uh, like for a wave function or something. It's absurd and it's ironic and it's low effort. So even though I like it, I'm going to put it in here. Okay, next one. Right, this is you'll pass the aux cord. You better not play trash. And then what you put on is Nima Arcani Kamed, one of the leaders in high energy theory, talking about the geometry of scattering amplitudes for no less than 11 hours. So I think this is some kind of summer school, and you can go on the YouTube channel that hosts these videos. So they put them in 1 hour segments, but they also put on the 11 hour kind of just everything. And Nima is known for just going on and on and on in talks. The guy never stops. The guy loves his own voice, and he's very passionate about sharing, I guess, his knowledge to people. And I mean, it's a meme because if he like if there's a talk after, then there'll always be over time, and so the next speaker will not have as much time to speak. But I guess this is a very egregious example in which, you know, the talk started at like, was it 3 p.m. or 4 p.m. and it just went on till like 2 a.m. which is just ridiculous. Like, can you imagine just sitting in a lecture hall and listening to someone talk about physics for 11 fucking hours? I don't know how the guy does it. But I mean, it's very insightful physics. He's probably the leader in scattering amplitudes in the field, and you're welcome to listen to it, form your own opinion, but it's just ridiculous. Not this is like this is an exception, by the way. This is by no means the norm. But I guess the meme is that if you're on a long road trip, like if you're going across the country from the U.S. from like East Coast to West Coast, this would do it for you. This would do it for you. This is a mid tier. Actually, kind of like, well, yeah. Let's put this. This is low effort. Let's put this in. Let's put this here. Okay, next one. Tech Bros in the 1940s. Okay, so this is a spoof on this is a spoof on the original. So the original is E equals mc squared plus AI. That somebody posted on LinkedIn, unironically. And he was like, you know, this consultant, I can suggest an equation has the potential to impact the future. E equals mc squared plus AI. The idea is that AI is like, by adding AI in the equation, it symbolizes the increasing role of artificial intelligence in shaping and transforming technology or something. So, I mean, this is obviously nonsense. This is obviously just like, why would you do this? It's like just putting a bunch of buzzwords together into something that just, you know, symbolizes kind of how AI is just like a hot topic. You know, name it and you'll get funding, sort of. Maybe not so anymore, but at least back in the day. And in the original meme, there was a guy who's from who did his undergrad at Princeton and at MIT. I think I actually TA'd the guy, but he was like, "What? Like, what the fuck are you talking about?" Right? And so the spoof is that there's actually an equation where AI is actually like not AI as in artificial intelligence, but AI as in just the letters. It's something that is actually in an equation. So I was like, so what is this? This is the partial derivative, and I is just, I guess, a coordinate. So the partial derivative tells you how things change, but then on the right hand side, on the left hand side rather, this is called the gauge covariant derivative, and this is what happens if you take the partial derivative and you basically add AI, you add the gauge field, and this covariant derivative, it tells you how quantities change in the presence of, I guess, some kind of like fiber bundle structure, some kind of gauge structure. For instance, if you have like a E&M field, then this object is, sorry, if you have a gauge theory, then so if okay, like, okay, how do I explain? If I can, so I can write down like the Lagrangian for a gauge theory, and for instance, E&M is one of these, but this has a gauge symmetry, meaning that each term in my Lagrangian should respect the symmetry, and if I just use the partial derivative, so for instance, if I consider this kinetic term, where I take the partial derivative of the A field, I guess, or I mean, how do people write? I guess it would be this. This is kind of an anti-symmetrized partial derivative of I guess what am I trying to do? Yeah, if I consider a term that's like this, so this is a 3-point vertex. I have a gauge field like a photon, and this gets coupled to a psi field and an anti-psi field, and this is a partial derivative because I need the indices to match. This is actually not gauge invariant. What I need to do is I need to upgrade this to a covariant derivative, which includes an instance of AI, an instance of the gauge field. And if I do this, the theory is well defined. There's a deeper reason to think about why you need this in the context of like fiber bundles. If I'm doing general relativity, then also like if I take a partial derivative of a tensor, it's not a tensor anymore. And so if I want the derivative of something to be a tensor, I need to add this connection piece. It would be some kind of combination of Christoffel symbols in GR. Right, but like, what am I saying here? The equation extends the derivative, the illustrious derivative, which measures the rate of growth into the complex. I mean, this is kind of like a spoof with the addition of AI. And in doing so, it transforms, it symbolizes the increased role in transforming gauge theories. It can unlock new forms of Lagrangians, true, enhance global symmetries. So when you have a gauge theory, you have some global symmetry that's enhanced into a local symmetry, and it can revolutionize all these things. So it's like, if you read this, kind of, it's in the same spirit of the original post. It's like, what the fuck? This makes no sense. You're extending the derivative to the complex plane. And this is demonstrated by Julian Schwinger replying over here, like, what the fuck? But this is actually like a legit, it's a legit equation. It captures the gauge covariant derivative, and you need this to make sense of quantities in gauge theory. So this is like, I mean, let's see. This is pretty low effort too. Let's put it here. Okay. Let's do something. So I don't think I made this either. Virgin contradictors versus Chad inductors. I mean, this is simple, but it's so good. Like, so this is obviously referring to two methods of proof. Like, if proof by contradiction, assume I'm wrong, then I'm wrong again. It's like he's always wrong. He's always kind of down, I guess. But or you can be like, if you assume I'm right infinitely. And this is a pretty simple, but I quite like it. Let's put it in. Let's put it in 8 here. Oh, sorry, wrong one. Let's do this. Okay, next one. Guys only have 4 ways out of academia. So obviously the original is guys only have 4 ways out of depression. Oh, that's already a spoof. But this is the original. You can go to war. You can villain arc, go to the gym. You can get a girlfriend, or you can find Jesus. I think the original is that this is supposed to be like a noose. There we go. This is the original. So the parody is guys only have 4 ways out of academia. You can be a finance bro, you can be a tech bro, you can be a defense contractor, or you can fucking kill yourself. And this is a big mood. Being a grad student who's in 4th year, I mean, it feels like, I mean, I would, I guess, like to continue to go to a postdoc, but it just seems that, like, I mean, there are many better ways out, especially in high energy theory. And of course, I mean, the 4th is, at least to me, better alternative than selling out, it seems. Can't go wrong with that one. I posted this, that there was a comment like, you forgot a 5th opt-in, which is working at McDonald's, and there was a comment below that's like, bro, that's literally the 4th picture. He's on its lunch break right now. Which is, I mean, you have this picture of I think this is Peter Parker from the Spider-Man movie. It was like urgently eating fries or something, like licking his fingers, but something like someone photoshopped a picture of him putting a gun in his mouth, and you can tell he just wants it so bad. It's just big mood. I like this meme, even though it's I'll give it I'll give it a high beat here. Okay, should we continue with the depressing grad student memes? Let's do it. I'm a 3rd year grad student versus I'm going into 19th grade. It's crazy, right? Because you do 5 years of I'm Canadian, so 6 years of elementary school, then 3 years of middle school or junior high, and then so that's 7 to 9, then 10 to 12 is high school, then you do 4 years of undergrad, so that's 6 plus 6 plus 4 is 16, and then if grad school is, so if you're in your 3rd year, then you're in 19th grade. If you're going into your 5th year, that's 21, which is 21 years in school from one to the other. It's actually ridiculous. Like, I mean, it's delaying adulthood, right? You're just, I mean, because you're in this, like, you stay in this school environment in grad school, you don't actually have to be an adult. Like, residence is provided for you, and a lot of things are just made nice for you in order for you to, I mean, this is not always true, and in fact a lot of grad students do get horrible treatment from their advisor or from their school, either financially or like professionally. It's very bad. But you don't have to like think about settling down. You don't have to think about buying a house, or like what a lot of what I think adulting really entails, right? You're still at the start of your career, I guess. And I guess this makes that kind of clear. So where did that go? I am going into there. I think this is probably here. Okay. Um, continue with the depressing grad school memes, or maybe not. Let's do something that doesn't take that long to explain. Okay, flag of German science if they never went fascist. Okay, so I always thought the arXiv, the you go here, and this looks a lot like the imperial German flag. Right. Okay. It's flipped. The red and the red and the yellow white are flipped, but to me it looked a lot like that. Um, and well, yeah. Obviously, the arXiv is American. It's funded by the Simons. It's held at Cornell. But I guess the joke is that if the Germans didn't elect a fucking fascist, then they would have still been the leaders in physics and science, right? Like Göttingen, where Hilbert and like all his contemporaries are. This was like the place to be. This is where quantum mechanics was developed. This is, yeah, the place to be if you wanted to learn about theoretical physics, at least in like the early 1930s. But then, obviously, yeah, with the fascists rise to power, after that, like German science was no more. They tried to expel all the Jews, that they fled to America, and as did a lot of other people just worried about the state of politics at the time. And if they hadn't gone that route, if this is alternate history, then I think it's quite likely that they would have, these kinds of institutions would have continued to preserve the lead. Like Einstein would have stayed there. I mean, Oppenheimer, he did his he studied under Bohr and people in was it, I think it was in Göttingen, right? There was Ehrenfest, so many luminaries of the day. And of course, this is also, well, maybe not of course, but there's this vexillology circle jerk, where it's like, often it's like flag of whatever, if whatever. So let me find an example. Jesus. Or like, it was like flag, yeah, flag of, this is a good example, flag of Sweden if Jesus died from an F-35. I guess another example would be this one, right? Flag of Norway, if it were a non-abelian gauge theory. And this is pretty low effort, not gonna lie. I'll put it here. Okay. Oh, what about this one? Okay, what's this about? So, like, let's say you have some process. Let's say the process is, so you have some kind of process. Let's say it's you have electrons and positrons scattering to electrons and positrons again. So the contributions of these there are different kind of ways this can happen, and one way, so these ways can all be represented with different Feynman diagrams. So this is one of them. This is called an S-channel diagram. These are all mediated by a photon, but then you can also have a T-channel diagram. Sorry, which is like this. So then you have the electron, you have the positron, plus E minus, so it scatters this way. And you can also have a U-channel diagram that looks like this, and these are all different contributions that you have to add. So, I mean, this is a simple example. There's an STU channel, these are called, and you have to add all the contributions. But if the process is more complicated, then there can be like tens of Feynman diagrams. I mean, at the research level, there are like hundreds that people have to each individually consider. And I guess it's a common student experience. I say this both as a student first, and then someone who's TA'd QFT like 3 times now, I think. Yeah, a lot of students will like be like, this is it, these are all the diagrams, and then there's another. I mean, this is confusing because Feynman diagrams are fundamentally like a combinatorial shortcut, and it's can be difficult to see where you like to make sure you got all of them. Kind of the thing I tell students is that Feynman diagrams, yeah, they're a way to diagrammatically represent Wick contractions, which is how you compute, I guess, moments about a Gaussian. You have some Gaussian ensemble, and you want to take moments of this, because that's fundamentally what you're doing in perturbation theory. You're expanding about a free theory, which is Gaussian, and if you're computing like a 2-point function, like a correlation function, here in a Gaussian free theory, in a Gaussian theory, it just comes down to computing second moments. But if you have interactions, then it's more complicated. You have to consider higher order moments. So always go back to Wick contractions. This is sort of the ground source of truth, and if you do this properly, you will not miss any Feynman diagrams. So this is also kind of low effort. I'm missing I'm skipping the S tier memes, I guess, because they'll take more time to discuss. This is maybe C tier. Okay. Oh, this is a fun anecdote. So actually, I was looking up some identities online, and I found this guy's site, which had them. So then I clicked on like the guy's. I was wondering who this guy was, and in his about section, he had this description, and it turns out that he was a student from the University of Toronto, which I was also in my undergrad, albeit like 10 years removed. So one day I was in the student union lounge. Oh, I guess back then it was physics and astronomy. Now it's only physics in McLennan Laboratories. This is the physics building of U of T, and he picked up a conversation between a guy and a girl sitting on a couch in a far corner of a room a few meters away. I heard the guy telling the girl that apparently there are objects called spinors that are even more general than tensors. I don't actually understand spinors, but I know enough to recognize that this is potentially misleading as stated. I could have jumped in and said something, as I usually tend to do, but I didn't want to hurt the guy's chances of impressing the girl, so I just let it slide. And so I thought this was just like a really funny anecdote, and I decided to make this. This is like your average freshman, Feynman stan who's like super, read his, what's it called? Surely you must be joking, Mr. Feynman, and be like, this guy's so cool. This is exactly what I want to do. I want to be this kind of like bro-y guy who also does physics because I'm smart, but doesn't actually know shit. And I mean, Feynman is like, I mean, I don't like the guy. I don't know if there's anything redeemable about the guy. He's a piece of shit. He's like egotistical and misogynistic, and just like I don't like. I don't know if there's any part of him that I actually do like, but yeah, I guess another thing that through his memoirs he's instilled that like this sort of idea that a lot of undergrads or high schoolers want to emulate the spirit, and what you get is like you have these like super bro-y freshmen or sophomores that think they're following in his footsteps, but they don't actually understand the physics of what he's talking about. And so this guy's trying to like rizz up a girl, average freshman Feynman stands. So there are these things called spinors that are even more general than tensors. So this is an experience that I think I've seen multiple times, and I've interacted with people like this in undergrad, and they're just like insufferable. But what can you do? I think a lot of this comes from Feynman's reputation as sort of like this playboy physicist that can hold office hours in strip clubs and hit on undergrads, just like do whatever, and he can get away with it because he's untouchable because of how good he is in the field. I don't think that's true. I think there are a lot of physicists who are better than the guy, both morally and in terms of being a scientist. So that's kind of the story underpinning that. Where was this? I think I can put this in like. I mean, this experience, it's hit pretty real. Let's put this in maybe high B tier. Let's say. Okay, so I did not make this, but this is I think one of the best and one of the oldest memes on high energy theory that sort of stood the test of time. When your grandpa tries to teach you Lagrangian quantum field theory, and you show him your 60-20 superconformal field theory, which is no Lagrangian description, is holographically dual to M theory on ADS7 cross S4, and when compactified on S1 gives 5D maximally symmetric super Yang mills. The future is old, young man. God, how to break this down? So the traditional way of doing QFT is through Lagrangians. You write down your Lagrangians and then you quantize it. This is what you learn in a QFT 1 or 2 course. But over the years, there are different ways of thinking about QFT, and perhaps quantum field theories or stuff that we want to think are QFTs that cannot be captured by this Lagrangian field theory. So let's try to break this down. 6D means you're working in 6 dimensions. You can do quantum field theory in any number of dimensions. But okay, you have super conformal. Oh my god, I can't write on this. Super conformal field theory. So field theory is just quantum field theory. Conformal field theory means that your field. So usual QFTs, they have Lorentz or Poincare symmetry, which are the symmetries of special relativity. They involve translations. Like if I translate myself by 2 meters, physics should, like the laws of physics should be the same, and the same is true if I do a rotation, and it's the same is true if I do a boost, if I go faster, if I change my speed, like a Lorentz boost. So there are, at least in 4 dimensions, there are 3 ways to boost x, y, z. There are 3 different kinds of rotations, and there are I could translate in either like 3 dimensions, x, y, z, or time. So that gives me 10. The symmetry group is this is called a Poincare group. It's 10-dimensional, and that's what a usual QFT is. So conformal field theory means that I give there are more symmetries, and one of these symmetries is dilatation symmetry. So if I zoom in, if I zoom in on my theory, then it stays the same. It's has this scaling symmetry, and there are these also called like special conformal transformations. So you can think of a translation as a point that fixes spatial infinity but moves 0, moves the origin. A special conformal transformation is a transformation that holds the origin fixed, but it changes where infinity is. So the usual Lorentz group in 4 dimensions, this will be, well, in D dimensions, this is called SO1D, and if you consider the group of conformal transformations, this gets upgraded to do 2, D. This is the group of symmetries of a superconformal field theory, but then you also have to take a product. It's actually like a semi-direct product with the space of translations, and so you have to do the same thing here. And when you have this kind of structure, you have a lot more to play with. Conformal, you might be like, scaling symmetry is kind of like weird, right? Like if I zoom in, maybe physics shouldn't look the same. And yeah, this is true. The number of conformal field theories are few and far between in the space of all quantum field theories. But if you have like any kind of many phase transitions at the point where, for instance, at the point where water boils, you can describe this using a conformal field theory. So that's CFT. What about S? S is super, meaning that you have supersymmetry. You have this symmetry that flips fermions and bosons into each other. So there is this like so this 2,0. This describes the type of supersymmetry. So this tells you that there are two supercharges. There are these two supercharges, and then the supercharges also form an algebra that combine with the conformal algebra into something that's very intricate. But that's what this is. You have a symmetry with like, you have a special type of quantum field theory that's like has a lot of symmetry. And this one in particular was found, I think, by Daniel Jafferis and collaborators like maybe 10-15 years ago. But people have not found a Lagrangian description that captures this. They believe that there's actually no Lagrangian description, but I don't know if there's a proof for that. And this theory is impressive because it has a holographic dual. This goes by the paradigm of holography. The idea of holography is that I can have a this is pretty amazing actually. I can have a theory of gravity in like d dimensions. So like let's say I have a theory of gravity in this kind of region, this d-dimensional region, this d-dimensional cylindrical region, and this can be a quantum theory of gravity. So this can include strings, it can include black holes, it's like fully gravitational. And here be dragons. But the holographic duality is the notion that I can have a gravitational theory that's dual to a theory without gravity, living on the boundary of the space-time. So this is a d-1 dimensional theory without gravity. And so what do I mean by dual? That means I can create a dictionary between them. Anything I can do in one theory can be cast into something else. The best example, the best known example of this is you can have what's called type 2b superstring theory, which is a string theory that describes gravity in 10 dimensions, dual to what's called super Yang-Mills living on the boundary of that. So I guess you start with type 2 superstring theory, and the background you consider is ADS5 cross S5. S5 is a 5-dimensional sphere. ADS5 is a 5-dimensional anti-de Sitter space, which is a space of negative curvature. This S5, this is a sphere, so it's closed, it has no boundary, but the ADS5 has a 4-dimensional Minkowski flat space boundary. And on that boundary you can put super Yang-Mills, so you can have a theory of like a non-abelian theory of like gluons, but that has a bunch of supersymmetries, and then anything you can do in one theory you can do in another theory. So this is the notion of holography, but that's only one example. There are many examples of holography. Another example is that you can have something called M theory, which is a generalization of string theory that resides in 11 dimensions. This is actually a very mysterious theory, but 11 dimensions. So you can put this on different, I guess, space-time background, classical space-time backgrounds. One space-time background you can put this on is ADS7 cross S4. So you're in 7-dimensional anti-de Sitter space. ADS7 cross SS4. And so if you go to the boundary, okay, so if I take ADS5 cross S5 and I consider type 2b superstring theory, then if I go to the boundary, this is dual to n equals 4 and describes the number of supersymmetries, super Yang-Mills. So that's the holographic dual of type 2b superstring theory on ADS5 cross S5. So similarly, if I take M theory, which is a theory that can sort of generalize many string theories, it lives in 11 dimensions, and if I take the so S4 again has no boundary. This is a 7-dimensional bulk spacetime. If I take the boundary of a 7-dimensional spacetime, I get a 6-dimensional spacetime, and so what I get is 6D2, 0 super conformal field theory. So that's what I guess this is a quantum field theory. It has no gravity that this meme talks about, but it's holographically dual to M theory on ADS7 cross S4. And if you compactify this if you compactify this in one dimension, like, so if I take one of these 6 dimensions and I compactify one of the dimensions, so basically I take the real axis and I make it periodic, I guess. So if I take one of the dimensions compact, so if I take one of the space dimensions and I instead make it periodic, I make it an S1, then what you get is you have 5D supersymmetric Yang-Mills theory, which is another QFT. This thing, I believe, definitely has a Lagrangian description. But so there are a web of dualities. I think if you make, so 4 plus 7 is 12. Wait, 4 plus 7 is 11, right? If you I think this should be, hold up, 60. No, yeah. I think if you compactify one of these directions, then this should take me from M theory to type 2b superstring theory. This is the gravitational bulk, and this is the quantum field theory boundary. These are all dual to each other. And I think there should be a way to compactify this 5-dimensional theory once more and get 4-dimensional super Yang-Mills theory. So this meme is just talking about a web of dualities between gravitational physics and non-gravitational physics that you can get by doing certain things. And this is like very fancy theory, right? It's got conformal symmetry, it's got supersymmetry, it's got multiple supercharges in 6 dimensions, it's dual to string theory, which is not a QFT. It's dual to M theory, which is even like higher generalization of string theory. So it's a very mysterious object. There's a lot of structures at play. Indeed, the future is now old man. Like if you showed this to Julian Schwinger or someone, like they just look at you as if you were insane. So this is the OG, I think, one of the OG high energy theory memes. It should be S tier. Okay. Yeah. Now that, okay, since we're on a string theory bend, let's look at smallest F theory gauge group be like. So my friend, I think he was on his way back from the airport or something, and he took this picture with a license plate that is SU207. So SUN, this denotes a Lie group. This is a special unitary group of size n. It's the set of size n by n unitary matrices with determinant 1. That's U means unitary, S means determinant 1, special unitary group of n. And so the standard model has a bunch of symmetries. This is based off the symmetry SU3 cross SU2 cross U1. So SU2 and U1, this encodes electroweak physics. This encodes the weak force and the EM, electromagnetic interaction. So you might be like the U1 is EM and the SU2 is the weak force, but it's not quite. There's some mixing involved. And the SU3, this encodes quantum chromodynamics. This encodes like physics of the strong force. And so you see these numbers are like super small, right? Like 3 and 2 and 1. And like, I mean, there are theories of grand unification where people think that the strong force and the electroweak force should combine into sort of one structure that's based on the group SU5 or SO10. And so this is grand unification, and these numbers are still pretty small. So in string theory, what happens is that you get some gauge groups that are actually bigger. For instance, I think there's like U to the 4. Oh, I'm offline. 496, I think, or like 128 to something like this. Like there's SO32, I guess, SO32. There's E8. There are string theories based off of E8 cross E8. E8 is this very big Lie group, lots of dimensions, and this can lead to exotic physics. But if you believe that string theory, if you believe that our universe is string theoretic, then somewhere there has to be like a set of subgroups leading you down from this big group to the standard model. But there's this in string theory there's this F theory constructions, which I don't really know that much about, but they're a way to get kind of more exotic theories, and kind of one notorious thing about these F theories is that they can give you very big gauge groups. And so the meme is like smallest F theory gauge group be like SU207. This is the set of 207, by 207 dimensional special unitary matrices. And kind of each independent entry of these matrices, they would correspond to something like a gauge boson, or some particle. So that's a lot of particles. And we don't see any of those particles, so it's like, where did they all go? People don't really know. So that's what this means. This is also kind of low effort, but I like it, so let's put it here. Oh my god, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, let's keep going for now. Let's do some more, and then we can do the rest later. Okay, this is kind of I quite like. When I'm in a worse QFT notation competition than my opponent is Steven Weinberg. So I mean, QFT is a tricky field, and there was a lot of mathematical machinery involved in that constitutes it. And so, like, no matter which way you do this, the notation will be kind of a slog to get through. If you're learning for the first time, there are various textbooks that people like to use. For instance, there's Peskin and Schroeder, which is one of the canonical QFT textbooks. There's Matthew Schwartz has one, which I like a bit better. And there's Mark Shrednecki. He has another textbook, which I think I like the most right now. But then there's like Steven Weinberg, who's like one of the goats in the field who's recently passed away, Nobel laureate, and he is like has a style of being just very meticulous, never making any mistakes, but he does everything his way, and he has 3 volumes of quantum field theory textbooks that they contain, like, if you read them, they'll contain basically everything you need to know. They're definitive. But one kind of downside is that his notation is absolutely horrible. So you can see this here. You can see this here. You can see this with. Okay, so what the hell even is this? This is the S matrix. So this encodes if I have some particles that are coming from past infinity, they'll interact with each other, and then there will be some new particles. There might be some particles that are created, some particles that get annihilated, but there will be new particles at the end with different quantum numbers, with different momenta. Okay, so what's going on here? So this is P stands for the momentum, sigma stands for the spin, N I think stands for the number of them, and so each of these correspond to the quantum numbers of one particle. So you can see the ingoing particles and the outgoing particles, and this S matrix tells you what's the amplitude of some in state going to some out state. And so here you have some Fourier factor. It's the sum of the incoming momenta minus the sum of the outgoing momenta. So this is really nothing. But then you have, so you can use symmetries, the Lorentz symmetry of the S matrix, because quantum field theory is based off of the Lorentz group. That has symmetries. Okay, so you can use this so lambda is any kind of Lorentz transformation, and so you can basically write this S matrix. You can relate it to an S matrix involved if the momenta are Lorentz boosted by some Lorentz matrix lambda. So this tells you how these two S matrices are related, and you have this factor that tells you how energies are boosted, but in addition you have these Wigner D matrices that tell you how because particles have spin, and a Wigner D matrix tells you how a particle with spin transforms with respect to some Lorentz transformation. So you have these horrible factors, and so like you have a lot of formulas basically that just are very complicated, that look like this. I think what the hell is this? This is I don't even know what this formula is, but I found these at some point and they're all bad. I think this is you have some. Is this some Klebsch-Gordon kind of thing? You have spin J, you have angular momentum J, you have spin sigma, and then these ABs are probably like internal indices. I don't know, man. So here you have a supersymmetric Lagrangian. So it's Lagrangian corresponding to some supersymmetric theory. So you have these G kind of super partners of gauge bosons. And then you have a spinner, you have more gauge bosons, you have something called a superpotential, you have all this horrible structure if you write this thing out in its full form. And it's just absolutely disgusting. Like, so there are a lot of reasons people don't like Weinberg's notation. I mean, it's not all this bad. I'm exaggerating. I mean, all these memes sort of exaggerate some kind of feature for humor. Oh yeah, and the fourth the fourth panel. This is the metric in a mu nu in QFT, which is flat. It's the Minkowski. So people either write -1 1 1 1 or 1 -1 -1 -1. This is, people could choose the East Coast versus the West Coast. The East Coast versus the West Coast. How to say? Convention. And which one really doesn't matter, but like gravity, people like using the mostly plus convention because so they use minus plus 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 because like this part, it's the same as like three-dimensional physics, and you just add a minus with which corresponds to time. But particle physicists like using plus, minus, minus, minus. This is nice because then people write p squared equals m squared. The norm of the form momentum of a particle is just its mass. In this convention, p squared equals minus m squared, which is like, why would, this seems kind of weird. So there are different reasons why people might like using one or another. Peskin, Schwartz, for instance, they use the particle physicists, they use the West Coast metric. Weinberg and Schroeder used the East Coast. And so, I mean, myself, I was trained as a phenomenologist, as a particle physicist in undergrad, and so I was like, this is the way to go, man, right? But this is not in theory. I mean, now I now do more theory. I work in gravity and algebras and stuff, where this metric is more common. And yeah, I agree that this is better because of various reasons concerning spinners and representations. But still, I my heart likes this metric when doing QFT, because yeah, p squared should equal m squared, not minus m squared. And so, this is me complaining about this, but because it's so complaining about Weinberg using the wrong side metric, but because it's so polarizing in the field, people have strong opinions about it. The joke is that I have been advised to continue this meme no further, because Weinberg is sort of definitive, and you shouldn't argue with him. So this is a pretty goated meme, I think. This is either low S tier or high A tier. Let's put it in S tier. What else? Okay, this is an easy one, I guess. I made this in undergrad. when you spot a mistake in your professor's notes, versus when you see the same mistake a few pages later. So you'll be like reading through some lecture notes, and then your prof's this like expert in the field, and then you'll be like, something's not adding up, and then you'll do some work convinced that you found a mistake, and then so it's like you think very highly of yourself for doing so, right? And so you're like, oh, I'll forgive you, it out of my magnanimous kind of compassion, right? I'll find it in myself to forgive you for making a mistake, and kind of just rolling your eyes back, like thinking highly of yourself. But then you'll see the same mistake a few pages later, where that same equation, say, is used in something else, and then you'll be like, what the fuck? Like maybe this isn't a mistake, right? And then so you'll do like an hour or two or longer of kind of just like making sure you understand, of deriving stuff, and then you'll you'll find out that it wasn't a mistake, that the prof was right all along, that you were wrong, and kind of undermining your sort of feeling smart for uncovering a mistake, right? And so this kind of jarring notion happens many times. Still happens to some degree when reading papers. It's pretty accurate. I'll give this a high A tier. Okay, now that we're on the topic of QFT, so I made this also in undergrad, I think. So there's a thermal physics, so when people are taking thermal physics for the first time, like statistical mechanics, or like intro stat mech, they use this book by Daniel Schroeder, and it's like super nice. It explains it to you very clearly, all the concepts very clearly, and never are you kind of fumbling, I think, in the dark, not trying to make sense of heads from tails. It's just like, it walks you all the way. It's very nice. And then there's Peskin and Schroeder, which is one of the canonical quantum field theory textbooks that's known for being very terse and difficult to get through. So it's like, if you don't understand something, you'll at least I will, like, it's, the book is berating you for, like, you fucking donkey, you, like, retarded piece of shit, like, what is wrong with you? It's not here to hold your hand. It's and you really gotta, like, spend a lot of sweat understanding what is going on. What I did not realize until some time was that this Schroeder is the same as this Schroeder. So it's like night and day, kind of the style of writing. And there's this Gordon Ramsay, right, is known for Hell's Kitchen being, like, super anal to his chefs, being, yeah, just like a not very nice. But when he's on a kids cooking show, he like if they mess up, he's very nice. He's there to hold their hand, make sure they don't cry, that kind of thing. So this is pretty low effort. Let's see, where did this go? Is it here? I would say this is like maybe low C tier. Okay, this is kind of easy to explain also. So Cecine pattern tensor. This is based on Margaret's Cecine pattern PEEP. It's treachery of images. So it draws a pipe, but then it's saying this is not a pipe. This is a picture of a pipe, and so it plays off of this this kind of dialectic. Yeah. And so it looks like a pipe, but it's not. It's just a picture of a pipe. And so here I've drawn a Christoffel symbol. A Christoffel symbol is something that encodes the curvature of space-time in general relativity, and it has three indices. So here I've drawn mu, nu, and rho, and it looks like a tensor, right? Because it has tensor indices. It has. I mean, when you usually draw a tensor, you draw it with, like, you give it indices, right? And that's how you know it's a tensor. But this thing actually is not a tensor because it doesn't transform like a tensor. It doesn't fit into a representation of the local SO1,3 group that plays that becomes the diffeomorphism group in general relativity. So it's misleading, and when students of GR, like, look at this to begin with, they'll be like, oh, it's a tensor, I can manipulate like a tensor, I can take derivatives of it, or I can take I can contract it with the metric, and, like, that'll still be a tensor. It's not. You need to add, for instance, you need to, like, add stuff to it. So for instance, like, if I have a vector, how do I say it? Nu, and then, let's call it lambda maybe. But then, so this will have to be lambda. And this will be nu. This object is a tensor. I have to take this piece, I have to multiply it by a vector or something, and I have to add it to, like, a partial derivative piece. This object is a vector. I mean, is a tensor. But these Christoffel symbols alone are not. So they are the connection for general relativity, in the same way that, maybe I erased it, but I had this meme that was like di equals d, this partial derivative, plus I, where this is the gauge field in gauge theory. So this thing plays the same role as this thing. I have to add it to something. I have to add it to partial derivative in order for it to be tensorial. That's it. Kind of dumb, but how to say it. It rings kind of true if you've been learning this for a while. Oh, yeah. I was gonna say tensor. In physics, people say a tensor is something that transforms like a tensor, and this is like, people don't like this. I think it's fine. It just, what people really mean is that when people talk about, like, say a vector is something that transforms like a vector, they aren't just talking about an element of a vector space that you'll see in math. They're talking about, you have some group that acts on some objects. For instance, rotations can act on objects, and then there are different ways that you can rotate something. There are different ways that you can rotate something, and for something to fall in one of these categories means that it lives in a representation of the group. It transforms under a certain way. So I guess this is what people mean when they say a vector is something that transforms like a vector. They mean a vector is something that falls into a representation of some group. It could be a rotation group, it could be a Lorentz group, it could be some translation group, it could be anything. But like, really, they're using the language of representation theory to talk about this. This is low effort, but okay. I kind of like it though. I don't know. I mean, a lot of this is pretty arbitrary. Maybe, yeah. Let's do that. Okay. So this is Star Wars meme. This is Vader killing defenseless kids. And this is like me, and then the nLab, which describes a lot of stuff in a very abstract way using category theory. Ernst Schreiber has a kind of unique way of thinking about stuff that, it's just super abstract. And so, for instance, they'll be explaining something like basic, but then they'll say from the n-categorical point of view. For instance, I could go to the carrying nLab, and they'll, carrying, like how people do arithmetic in grade school, and then they'll mention talking about commutative algebra or cohomology, some d-looping groupoid, and some, what's it called, Postnikov tower, and it's just like, just absolutely kills you. There's no hope in you trying to understand it, which is a common experience also in the field. I quite like this. I mean, there are a few nLab posts, I think. I think this might be my favorite. Are there more? I think that's it for now. Let's put it. It's not maybe here. Yeah. Let's put that there. Oh, this is a fun one. My brain when I wake up in the morning. So this is inspired by a real story. I was reading Haag's local quantum field theory, and they were talking about KMS states. KMS is short for Kubo Martin Schwinger, who discussed this. And this is a way that you can sort of generalize the notion of thermality. So usually when you're you have something, you're in a thermal system, what happens is that you have some Hamiltonian, and you have some beta parameter, which is like 1 over temperature. And if you want to compute something in a thermal ensemble, then you take some operators O1, O2, and then you take their expectation value, except you add this instance of e to the minus beta h, and this wouldn't correspond to you're in the canonical ensemble. Well, more generally, a state is just a way of taking some operators to numbers, or complex numbers, real numbers, I think. Yeah, and so this is an operator in like a quantum theory. So for instance, one of these is like a vacuum expectation, right? This could take an operator to the expectation of that operator. For instance, in quantum mechanics, you can look for the expectation value of the position operator, for instance, about a quantum harmonic oscillator. Well, that's one example of a state, but a state is more generally something that takes operators to real numbers. And there's a way of formalizing a thermal state, and this is the following. If I have operator A at time t, and I have an operator B at time t plus, then if you have a state that satisfies, I think it's like this, plus beta over 2, I beta over 2, times A of t. This is a thermal. This is a KMS state, and it generalizes the notion of thermality. The way that you can see this is that if I have A at t, this would be like Heisenberg operators e to the IHT, A e to the minus IHT, and you have B similarly e to the minus IHT. And for instance, if you're computing a thermal state, then you have this, and I'm taking a trace over all kind of quantum states. Well, I can use the cyclicity of the trace to move this object here, and then I can multiply and divide by some copies of minus e to the minus beta ht, and I can group these together in the exponent. And so, oh, maybe this is not 2, maybe this is just t to the I beta. And so you can see that this satisfies this KMS property. So this is true if I know what the Hamiltonian is and I know what all the microstates are. More generally, the Hamiltonian can be not a well-defined operator, so you can work with this definition instead. And this is kind of something people do in the paradigm of algebraic QFT, KMS states. So what else is said? Yeah, so you're given a dynamical system, some time evolution, and some operators that form an algebra. Yeah, and so people talk about different KMS states that give you a notion of thermal equilibrium, I guess. But yeah, I was opening this in the morning, and all I saw was fucking kill myself. So I quite like this. I'm gonna give it an A. Maybe here. Okay, let's also, okay, what's this one? Oh yeah, another starting the day meme. Every day, on the arXiv, hep-th, there are like 20-ish papers, 30 papers that people, it's good practice to peruse, see if any of them are relevant to your work, and so it's like all the tabs are celebrating that they're open. There's this, in the spirit of this, I guess. But it is tiring. It is tiring having to do this every day and worried about getting scooped every day. This is pretty low effort. Maybe here. No, but it's yeah, okay. There's this one. September 11th, there was a arXiv had a DDoS attack, and so it's like a Bush meme about 9/11. This is pretty low effort. I don't know why this is even here, but I will add it to here. Okay, now there are some heavy hitters. Let's open this one. So SUSY is beautiful motherfuckers when I make them write down the simplest supersymmetric Lagrangian they know. It's like, and it's like super complicated. So I guess this is based off the thing that like people are like, oh, supersymmetry is so nice because it unites all forces. It solves a bunch of problems, and like it's elegant that every particle has a super partner. You can do stuff in superspace, and it's just very nice, I guess. But then if you write down any supersymmetric Lagrangian, as you saw with the one in Weinberg's, you saw the one here, it's like ridiculously long and complicated, and so it's like they're kind of coping before being forced to write down something that takes like 2 pages. This is an A-tier meme. I like it. Let's put it here. Okay, you can keep going. This is a fun one. Okay, so this was made, I think, super long ago when I was in like freshman year or something. But I mean, you know how people say, right? The sum of the sum of integers from 1 to infinity is minus 1/12, and this is like obviously like nonsense. The way to do this properly is the sum of they write this as like they define the Riemann zeta function of S as n to the s, right? So then, wait, is that right? Yeah. So this thing is well defined when S is like negative, but then when it's so then like this defines there are other ways to define this also, but it's like a holomorphic function or meromorphic function. It's analytic except in some regions, and so you can study this as a complex function of S, and then this function takes on a value at 1 when S equals 1, and then that makes people go like, oh, the sum of natural numbers from 1 to infinity is actually it's minus 1/12, which is that value, and people actually use this a lot in string theory. So for instance, if you have some kind of 0 point energy and you have an infinite number of modes, then you have to, if you want to manipulate this, then it's formally divergent, but one way to regularize this is if you use this kind of Riemann zeta regularization. You can find it in like any QFT textbook or like any string theory textbook. And so at the same time, someone just made a cool, like this cool S symbol in LaTeX, which is pretty cool. And so that kind of inspired the meme, like, oh, broke the average, the sum of integers diverges, bespoke cool S of integers is minus 1/12. And I guess this shows that this is not a sum, this is something that's different. It's obviously this is true. If you want to make any sense out of this, then you need to do something that's different. I like this too. Let's give it, I don't know if it's an S tier. Wait, maybe something like this. Okay, another grad school experience. Crushing onset of imposter syndrome caused by a rogue minus sign. This is so fucking real. I don't think I made this, but yeah, like you could be doing this calculation and trying to find this minus sign for like hours or days, and like just not being able to do it, getting the wrong thing, not feeling like not being able to do something that you should be. That's very basic. It can make you feel like dog shit sometimes. So it's a basic meme. It's a simple meme, but I'm gonna give it S tier. Okay, so let's do this one. Um, I mean, what do I say? I think the original was like, what was it? It was something like, yeah, something like this. So you chop off the T, and then it's like, people thought back in the day that Yang-Mills was non-renormalizable. It was plagued by these infinities in a way that like you couldn't get rid of, and so the theory was sick. Until a guy called Gerardus Hooft. It's a Dutch name, so it's you have this kind of, I'm not sure what it's called. I think it's short for het or something. But like, yeah, you chop the T off, and instead you keep this. And Hooft was able to show that the theory was renormalizable. This is also pretty low effort. Let's put it here. Stack overflow motherfuckers when their kids are identical twins. They're marked as duplicate. I guess one's gotta go. I mean, this just, it speaks to the fact that like the moderators on Stack Overflow are like super strict and anal. If you know, their goal isn't to help you answer questions. Their goal is to compile a repository of like questions that people have that show up on the first page of Google search. And so literally like duplicate questions, if your question is like, you know, they think it's dumb, they'll like roast you for it, and it's kind of going off of that. This is also pretty low effort, but I think it's I quite like it. I mean, I'm quite fond of a lot of these. Okay, another I think I made this in undergrad. Rick and Morty. So the original is like, let's go in and out, 20-minute adventure, and they come out like 3 days later, just losing their shit. So, you know, you think the problem set isn't too bad, like, oh, it'll take a day, let's do it, grind it out, you and a friend, and then, you know, this is you like 2 days later, 2000 kind of console commands, and later in Mathematica, just like wanting to, just like hating yourselves, wondering why you chose to do what you're doing. This is also pretty relatable. Where did this go? Maybe here. Yeah. Am I saving? Okay, I'll save some of the best for last. Okay, so this is, I didn't make this. I don't understand that much about this, but like this is roasting condensed matter, like people who work in condensed matter theory. So this is like, yes, it's a mix of quantum mechanics and stat mech. Actually understands neither, is actually chemistry. I mean, that's not really true, but even neutrinos have more human interaction is pretty good. Basically a human fermion. This is why I think this meme is here, because you know, by Pauli exclusions, fermions they can't occupy the same quantum state. It's like against the laws of nature, and so you never see them in pairs. They're always isolated alone, and this gives fermions a lot of interesting physics. This is what inspired my Twitter handle, or just various handles I go by online. I think human fermion is pretty accurate. Yeah, they try to reduce a lot of problems to band theory. I mean, okay, I guess this is saying that, you know, like they're working at super extreme conditions that aren't representative of reality to, like, you know, find some exotic state of matter. This is like bosons are Cumming. They're condensing into condensed Bose-Einstein condensate. This is pretty mid, I guess, but I do like human fermion, so let's put it here. Okay, now some of the hard hitters. Okay, let's do this one. Okay, so hep-bros keep Wick maxing. Hep refers to high energy theory. Wick refers to Wick rotations. So there are two ways that people can do quantum field theory. One is you work in Lorentzian space, where the signature has sign, I guess, minus plus 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 or plus minus minus minus, and there's another way where you basically work in imaginary time. You work in tau, which is I times t, and if you do that, then the metric becomes plus 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 plus, which is Euclidean signature. And so, I mean, this might seem like a weird operation to you. This is called a Wick rotation, because you're rotating time 90 degrees into imaginary space. But they're different. These are two different ways you can do physics, and the claim is that Euclidean field theory is a lot better. I mean, I talked about one of these, so you can have hep-foids, which I like that wordplay. It's plus minus minus, and people who are gravity gravicells are like, no, it's the reverse. Well, in Euclidean field theory, it's unambiguous. Then it's just plus 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 plus. And another reason that this is bad is because, well, it's not bad. It's just like people don't like. It's that so in Lorentzian field theory, the path integral looks like this. So you're summing over all kind of field configurations, but you weigh it by an imaginary number, a phase, and so if they constructively interfere with each other, then the probability gets enhanced. If they destructively interfere with each other, which happens generically, it doesn't get enhanced. But the problem is that for generically large field configurations, this integral will wobble like super wildly, and so this you can't define it rigorously, and so yeah, the path integral in Lorentzian space has no mathematical definition. Well, it's not well defined, at least so far. People don't know how to do it. If you do a Wick rotation, this I becomes minus. So for complicated field configurations, the action is very big, and so this is highly suppressed. When this happens in like statistical mechanics. If this is like e to the minus beta h, then you can make sense of this integral over all field possibilities using the Feynman Katz formula. So that's another reason why the Euclidean path integral is good. So like something people try to do is people try to put theories on the lattice because a computer can do them. What do we mean by lattice? By lattice, I just mean like some kind of grid, right? And then on you put degrees of freedom on the grid, and then degrees of freedom can interact with each other. But if you do this using Lorentzian field theory, then it breaks Lorentz symmetry, because if I make a boost, then the lattice just gets like horribly distorted. So I can't work with lattices in a way that preserves Lorentz symmetry. Euclidean field theory, however, is much nicer. It's defined on the lattice. I mean, sure, like it partially breaks translational invariance, but it only breaks it up to mod something, and I guess it can break rotational symmetry, but still you can define theories on the lattice using Euclidean field theory. This is how all of like lattice field theory is done, which has its own category on the arXiv. Let's see. So how oh yeah, I guess I mentioned this here. If you make a Wick rotation and you have e to the minus s, well, if you compare this to e to the minus beta h, which is the partition function in statistical mechanics, and you sum over all of the microstates, this is z. In statistical mechanics, this is the partition function in quantum field theory after Wick rotation, and they're basically the same. So it connects QFT to statistical field theory, which is a very nice thing to do. Um, what else? So I'm not going to explain what modular invariance is, but there's this nice property of correlation functions that is manifest that's not at all in Lorentzian field theory. People just compute S matrix elements all day, I guess. Um, in Lorentzian field theory, which is kind of boring. Okay, how to explain this? Yeah. So another thing people do in quantum field theory is they compute correlators. And so, for instance, if I have a field here and I have a field here, basically if I wiggle the field at some x location x prime, how does it affect the field at location x? And this is problematic because in the quantum theory, these fields, they don't commute. So it's like which correlation function are you talking about? Are you talking about this one? Are you talking about the one with x prime here and x here? There are different correlation functions you consider. There's called a time-ordered correlation function, which is like t minus t prime psi of x prime. So like if t is greater, so this is time ordered. So if t is greater, then you put t first, and if t prime is greater than t, then you go the other way around. And so there are a bunch of correlation functions that people can write. With 3-4 point functions, they're even worse. They're time ordered, retarded, Riemann correlators, like all these different correlation functions. Don't even get them started on 3-point functions. But in Euclidean signature, all operators like commute. And so you can ask how do these ordering ambiguities arise when you go from one theory to the other? Well, it's kind of as follows. So let's plot time, or let's plot t. Let's plot tau. So this would be Euclidean time, where it's imaginary, and this would be like Lorentzian time. So if you compute, like you can look at the analytic structure of a correlation function, and what you'll find is that this has branch cuts on the imaginary tau, or the real time axis. And so here the correlation function is free of branch cuts. But if you want to say, what is it valued at, like t equals 2, then you have to either choose to go this way around the branch cut or this way around the branch cut. And all these branch cuts lead to different kind of prescriptions of non-commutativity. So, but if you work over here, then your theory is like super simple. You don't have to worry about operator ordering ambiguities. So in Lorentzian field theory, time evolution is unitary because you go like e to the I h t. Right, obviously this is a unitary operator, but if I go from t to tau, then the I cancels this. And so this is time evolution. So if I acted on a state, that's a combination of energy eigenstates. Like let's say alpha n, give it some coefficients. And this is the energy eigenstate. Then because of linearity, this will be minus e to the n times n, and so when e to the n times tau, so when tau is like super big, then all of these will be super suppressed compared to the vacuum state, the state with the lowest energy. And so time evolution will kill all but the vacuum state, and this is very important if you want to like prepare a state using the Euclidean path integral. It's very good for that. So also, the Euclidean theory you can also use to study instantons. So instantons are saddle points of this action. So the saddle points are sort of the points where the correction, how to say, like I guess there's an h bar in all of this stuff. So if you want to approximate what this partition function is as h bar goes to 0, then this picks up a contribution over saddle points of S. And the saddle points correspond to solutions that tunnel between different vacua. And you can see this in the Euclidean picture, but it's very hard to see this in the Lorentzian picture. So that's another reason why the Euclidean path integral is very nice. And finally, you can study this for gravitational theories. So the Lorentzian, I haven't seen anyone like use the Lorentzian path integral for anything gravitational. It's like, it's good for nothing. But in Euclidean field theory, it has like sort of forbidden knowledge. It has knowledge that you think it shouldn't have. It gives you access to like black hole entropy, to the Ryu-Takayanagi formula, which is this formula that connects the holographically the entropy of regions in the boundary to the minimal area surfaces in the bulk. It gives you page curves, which tells you how black holes evaporate, how the entropy increases and then decreases. It's really amazing, and some of these are like very new developments in the field that you wouldn't expect something as innocent as the Euclidean path integral to have, but yet it gives you access. So this is like a pretty good meme. Let's see. Maybe here. Let's say. This is an A tier meme. Okay. So there are some things that will take a while to explain. Okay, let's this is, I think, pretty. No shit. Oh shit. Oh no. Okay. That's unlucky. I'm back. And yeah, I accidentally deleted this page, but I restored it. So let's keep going. Do you want to read some Faulkner this summer? From a friend, thinking he meant like William Faulkner, As I Lay Dying, Sound and the Fury, Absalom, which I really want to read more of. He's very good, and no, he means Thomas Faulkner's papers on von Neumann algebras, which is something in my field that I should do, but just haven't. This is a pretty low effort meme, not gonna lie, but yeah, let's put it here. This thing got duplicated for some reason, and I can't get rid of it. It's fine. Let's keep going. Let's do this one. When the Banach space unit ball is non-compact, visions of the utterly deranged. So this is like people trying to envision a oh god, so some biblical angels, right? Some like really weird shit that's supposedly like esoteric and stuff, but okay, so what does this mean? Well, you can basically picture balls in different dimensions. In 0 dimensions, you just have a point. In 1 dimension, it's a circle, and 2, it's a sphere, or like a disk, or the internal, like the inside of a sphere, I guess. And you can do this for higher and higher dimensions, but the higher more dimensions you go, the less intuitive this ends up being. And in particular, you can think about what the unit ball looks like in infinite dimensions, and it's not even compact. So in finite dimensions, in Rn, we have this Heine-Borel theorem that's like closed and bounded means compact, but this is no longer true, and so you can get some very weird properties, very messed up properties that are actually they end up being quite important in like analysis and QFT through the structure of one-normed algebras. So Hogg talks about this in his local quantum theory, chapter 3 or something. You can take a look if you're interested, but it's like very weird. This is I'm quite fond of this meme. It's at least a high beat here. Okay. This is an easy ask here. So, effective field theory alignment chart. I could honestly make a whole video about this. I have gave a recitation about this in QFT, and that took like an hour. So the idea of effective field theories are that there's interesting physics at all scales, and so you can construct these field theories at all scales. For instance, if you work with the standard model, not all of the degrees of freedom will be relevant to low energies. Like, you don't need to know the top quark mass to build a bridge. And at some point you can integrate out all the super heavy particles that don't play an importance, so you're left with lighter particles. So for instance, if you're working with quantum electrodynamics, like if you're in a lab working with optics, just like matter and electrons, you don't need to worry about like the weak force or the strong force or like the gluons or like any of that, right? So you can integrate all of those out till you're left with just quantum electrodynamics. And there are various effective field theories that you can write down. This can be like in quantum field theory. It can be more generally, it can be like a physical field theory that is not necessarily a quantum field theory, or it can really be a theory of anything. And something else that you need is a power counting parameter, which tells you that when certain like higher order contributions can be suppressed. So the purest take is that this has to be a ratio of energy scales. For instance, the ratio of like weak physics to the energy physics that you're interested in, or it could be just any ratio of dimensionful quantities, or it could just be anything. It doesn't have to be like right. And so there are some examples. So for Fermi theory, this is the idea that Fermi developed it. It was a theory of neutrino decay. Back before people knew about the weak force, so you had a muon decaying through this vertex to an electron, a neutrino, an electron neutrino, and a muon neutrino. So in the standard model, this would be mediated through a Feynman diagram that looks like this. It would be through a W boson exchange. And then these particles will be the same. But if you zoom out, you can see how this kind of, this thing just becomes this thing. Just becomes a single vertex. And you don't know necessarily what's the underlying physics for this vertex. You just know that something like this vertex exists. So you can do some measurements. You can get the properties of this vertex, and then you can just use this in your theory. So you don't have to care about the W physics, the electroweak physics that's undergirdering this. So this will be valid. So let's say you're measuring muon decay at some energy. Let's call it E. And the scale of the W physics, of electroweak physics, is going to be the mass of the W boson, which is like 80 GeVs. And so when you are at physics, when E is way less than W, with the W mass, this is a good approximation. So this object, this ratio, is your power counting parameter. And if you don't want to work with the W boson in its full generality, you can pick up higher order terms in this power counting expansion that will let you work using the 4 Fermi theory without having to do electroweak physics. So another example is soft collinear effective theory. So this governs how different sectors of QCD interact. For instance, if you have two beams at the LHC that collide and they create like they create stuff, then what you really want is you want to choose two directions, and you have different collinear sectors of QCD, and each sort of you pick a direction and you see how that direction of momentum scales for different particles, and so that's sort of the power counting parameter. If it's big, it corresponds to hard physics. If it's small, it corresponds to like soft physics. And so the power counting expansion for SCET can actually be quite complicated, so we won't get into it, but you get these cool looking Feynman diagrams. Another example is large and QCD. So QCD, at least in scales at like the proton level, it's very non-perturbative, it's very complicated. And so for a lot of time, people didn't really have any traction over it because it's strongly coupled. You can't expand it around some free theory. But there was this 1 over n. So if you have a SUN theory, you can expand around 1 over n. And if n is very large, this is quite a good expansion. For QCD, n equals 3. So the power counting parameter is 1/3. But so it's not great, but this allows you to get traction on some non-perturbative physics, like for instance proton, like baryons and mesons, their spectra. So it's very it's pretty cool. And this also has string theory realizations, I guess. So now, okay, it doesn't have to be quantum field theory, it can be any physical field theory. Well, general relativity is another example. When you're writing down the Lagrangian, people usually just write this term. So the square root of the metric to make this thing for the volume element, but then people add the Ricci, this is the action. People add the Ricci curvature, but you could also add like something like the Ricci curvature squared, or you could do r mu nu rho sigma, r mu nu rho sigma, like take the Riemann curvature tensor and contract it with itself to get the Kretschmann scalar. But then these terms will be Planck mass suppressed, and so you can think of this as the power counting purist being like a ratio of energy scales between the Planck scale and whatever scale that you're considering. So because the Planck scale is so far away, then the first term is a pretty good approximation. But in practice, you would have to, I mean, like in theory, you'd have to keep all of these, and that's why general relativity is an EFT. You can also consider the multipole expansion, which is something that, like you have an electric, you have some distribution of charges, and just like, ordinary electrostatics, but then you want to know what this field looks like far away, and so the first moment is a monopole moment, so this will fall off as 1 over r, and what you care about is the total charge. So for instance, you have 3 negative charged particles and 3 positive charged particles of the same magnitude. This will vanish, and then you have a dipole moment. I guess this will be 1 over r squared. This will be 1 over r cubed, and the dipole moment corresponds to some like, usually like you have a dipole. You have a positively charged and you have a negatively charged particle, but this distance is like, you take this distance to be 0, and because of this, the suppression is of the electric field is not 1 over r squared, but rather 1 over r cubed. And you can also have a quadrupole moment, which would look something like this. So you have 2 positively charged and 2 negatively charged particles. Like the dipole moment is 0, but there's this quadrupole moment, and this would fall off as 1 over r to the 4. And the power counting scale is the size of the charge distribution compared to how far away you're looking at it. So this is also it's a physical field theory because it tells you about the electric field, but it's not necessarily a quantum field theory. And okay, Euclidean gravity. So this is like gravity. You're looking at gravity from the point of view of the Euclidean path integral. So then you have to sum over all the, because you have to integrate over the metric in the path integral, you have to sum over all topologies. And so topologies that have higher genus will be suppressed by the Euler characteristic. And so that e to the minus Euler characteristic gives you like a power counting parameter. Now we can go to subject rebel. You can talk about string theory as an EFT because it arises effectively from some mysterious M theory. Notice how I say it's not physical because, well, it's kind of tongue-in-cheek jab at the string theorists. So the hydrogen atom is actually also an EFT because so like kind of at zeroth order you just have an electron kind of cloud about a proton, but then the electron has a spin and the proton also has a spin because it's composed of two up quarks and a down quark. So this is a contribution that you have to take into account. But then also, if the electron is spinning fast, then you have v over c corrections, the velocity over the speed of light, and so all these. If you have a magnetic field, then this can cause a splitting between a farther splitting between these two spins, and so this corresponds to like the Zeeman shift, the Lamb shift, all of these parameters that you have to account, and the power counting parameters would be like v over c, and because magnetism is fundamentally a relativistic effect, and a lot of complicated stuff that can change the fine structure, hyperfine structure of the hydrogen atom spectra, like the amount of energy you need to dissociate this electron from the hydrogen atom, like spin orbit coupling. That was the one, due to the spin and the spin interacting. But then you can have magnetic field effects. You can have relativistic effects. It's like, you'd have to take it into account, all of them. You can also study neural networks from the perspective of field theory. So here the power counting parameter is 1 over the width being the number of nodes in each layer. If it's infinite, then the neural network becomes like a Gaussian theory, and it's easy. But if you consider 1 over width, you can work in powers of this, and you get people write cool papers about this, studying neural networks from effective field theory techniques. This is an S tier meme. Okay, what else? Okay, am I gonna explain this? I live in spin, but the S is silent. So, okay, this is based off the meme. I live in Spain, but the S is silent, so it's like I live in pain. But this has to do with the spin group. People can talk about the spin group in n dimensions, and this governs how fermions behave. But then there also exists something called the pin group, which is that what happens. This characterizes how spinners behave if you also let the orientation of the transformations you care about being reversed. And so spin is to pin as SON is to n. This is the special orthogonal group with determinant 1. This is ON. And so it's kind of dumb, but yeah, this is how fermions are representations of the spin group, and you can upgrade the spin group to a pin group if the S is silent, and then you don't get spinners, you get something that are called pinors, which you need if you want to characterize how these particles behave under orientation reversing Lorentz transformations. This is like low, maybe here. Yeah. You can call me a simple algebra because I ain't got no ideals. Super deep fried picture of Bugs Bunny as a mercenary or something. Simple algebras are the algebras that have no ideals. An ideal is basically something like a sub Lie algebra you can consider. This I didn't make this also, but it's okay. It's pretty low effort. Let's put it here. Okay. Next one. Right. So, using the Atiyah-Singer index theorem to analyze Fermi zero mode, it's kind of like nuking mosquito. So, so pions correspond to quark anti-quark. So let's see, how does this work? There are these triangle diagrams. So you can have a pion entering this. You can have a pion, kind of neutral pion, doing its own thing. But then it interacts with the axial current of QED. And so you have this Feynman diagram where you have like some quarks floating around in here. You have a quark loop, and then this decays to 2 photons. So you'd think that people back in the day thought that this decay is forbidden because of conservation things, but it's actually allowed because of something called the axial anomaly. And an anomaly is a symmetry of a classical theory that is not a symmetry of the quantum theory. And the reason that this happens is the path integral measure is not invariant under the symmetry, and so you need to Noether's theorem basically needs to be modified. You have a current that is no longer conserved, so you can have a current corresponding to the flux of pions, and this is not vanishing, which means that pions can decay, and the decay is mediated by this kind of Feynman diagram, which is exact at one loop. It does not pick up any higher loop corrections. This is due to the presence of Fermi zero modes of these fermions in the middle of the loop, and so you can study this mathematically. There's something called the Atiyah-Singer index theorem that tells you how like the magnitude of this decay is, and it can be like a lot if you haven't seen these things, these index theorems in practice, or K-theory, and so yeah, this is a common experience. This is maybe B tier. Yeah, 1, 2, 3, 4, 5, 6. Okay, 7. Let's do this. This is also so. Euler angles are used to parameterize rotation groups, and if you look up Euler angles, this is one thing that you learn once in undergrad, and then you're like, never again. I'm never going to use these again, because these are like super like just messy, and there are cleaner ways to deal with rotations. Why would anyone use something like that? But I'm working on a project where you can actually use these to dealing. So I'm working in it's a project in two-dimensional de Sitter space, where let's see, where if you have a field, if you have a matter field in this background, then it falls into some SO2, 1 representation. So this is kind of like a rotation group, except one the signature of the metric is different. And so here Euler angles actually save your ass. They can make a lot of very non-trivial manipulations of the wave functions obvious. And so this is going, maybe I treated you too harshly. Mm, maybe here? Yeah. Okay, this is also a low effort meme. Um, yeah, so vector, tensor, spinor, twistor, torsor, phasor. I thought a phasor was going to be some kind of cool representation theoretic thing or particle theory thing, but it's just some like notation that electrical engineers use in calculating inductance and impedance and all of these things. This is low effort. This is uh somewhere here. Yeah. Okay. Let's do this one. This is a big one. Okay, so this is comparing holography to, so there's this notion of Plato's cave, right? Like people in the cave, looking at fi- uh, looking at pictures on the wall will start to think they're real, and so this is a spoof of those stop doing whatever memes that is, I'm applying to like studying quantum gravity from the point of view of holography. I mean, so this sounds totally bizarre that you can have theories of gravity in d dimensions that are dual to um, theories that are in one lower dimension without gravity. So you can have like a bulk ADS space that's dual to a boundary CFT, and if you have something that's moving in the bulk ADS, it's dual to something in the boundary, and then there's this entanglement wedge reconstruction. This is Maldacena in the meme. He's like this trying to trick you into believing that this is real, and of course you're the soy jack that buys all of it up. So it's like they've played us for absolute fools. This is like, how is this real? But it actually is, so it's incredible. But so general relativity and quantum information were never meant to be combined. Years of anti-de Sitter, so this is working in spaces of negative curvature, which holography was founded in. But like people haven't been able to. So you can show that there are ADS physics in ADS spacetimes that's dual to holographic physics living on the boundary of that space-time, but de Sitter space has no boundary. It's a closed universe, so it's like, what's if you want to formalize holography for de Sitter universes, which we live in, right? We live in lambda CDM de Sitter universe with the positive cosmological constant. How do you know? What are you going to do? And people don't know. Want to quantize gravity for a laugh? We had a tool for that. It was called perturbation theory. So you work in powers of G Newton, I guess. But this is bad because the effective field theory breaks down at Planck lengths, and so this is saying some things that seem absurd. Can I have something entropy square meters of LAN? This is poking fun at the Takiyanagi formula, where you have an entropy of the boundary theory. That's A over 4 pi G Newton. So the entropy of this region in the boundary is actually dual to, you can compute it by this the area of this minimal area space that's homologous mod by 4 pi G Newton, and this is actually related to these Bekenstein-Hawking black hole entropy formulas. But yeah, okay, am I going to explain this? Bulk locality is a geometrization of emergent type boundary type 3-1 subalgebras. This is this is a discovery by my advisor and his former student, I guess. This is saying that the fundamental degrees of freedom are not geometry, but they're really algebras of observables, I guess, or just quantum information. And one way you can study quantum information is through algebraic QFT. And through holography, locality provides sort of like a geometric manifestation of these subalgebras, these type 3-1 von Neumann algebras that emerge in some limits, which sounds totally weird. Like, what the hell are you talking about? type 2b string theory. So I talked a little about this on ADS5 cross S5 is dual to n equals 4 super Yang-Mills conformal field theory. So you have a string field, you have a string theory, not a string field theory. You have a string theory in the bulk that's on the background ADS5 cross S5. So you have a 5 dimensional sphere, and you have this is Cartesian product with ADS5 space, and this is dual to in 4-dimensional theory with maximal supersymmetry. It's a Yang-Mills theory living on the boundary. So it's like, this is crazy. This is sort of a tensor network. This is, how do I explain? So this tells you how information is encoded in the bulk, how the boundary information is encoded in the bulk using these tensor networks. So there's this kind of quantum error correcting codes at play. This is this is a replica trick Euclidean wormhole that is involved in the calculation of bulk observables using the Euclidean path integral. This is a entanglement surface. This shows you how where boundary information is encoded in the bulk. So that's holography. I think this is an S tier meme. Okay. This is also low effort. Why don't the Eagles just wormhole from the Shire to Mordor to drop the ring in the volcano? This is based off like why didn't the Eagles just fly to Mordor to drop the ring? Why do they have to go the long way around in the Fellowship, whatever? But also it's like how, wormholes in sci-fi movies, they're like in order to explain, it's like you take a piece of paper and then you poke a hole to like show how you're changing the space-time metric to create something that can, I guess, tunnel you from one point to the other. And it's saying that both of these are just like dumb critiques. I quite like this, actually. This is a B tier meme, I think. Let's put it here. I mean, don't take it too seriously. Yes, okay. Here a quantum field theory is defined by a monoidal functor Z from the Bordism group from d dimensions from some kind of manifold to a vector field. Yeah, from a suitable monoidal category of cobordisms to a suitable monoidal category of vector spaces. Wasn't sure quite I'd seen, but it knew it was time for me to leave. So this is one way of formulating topological quantum field theories. How does this work? So you have some Z, which you think of as a partition function, and it takes you from a Bordism group. So, okay, so all this is dressed up in the language of fancy categories, but that's I think a bit overkill in my experience. So you can have like two, I think, let's see, how does this work? So this is, say d equals 2. Do I remember how this works? You're in 2 dimensions, and you have some manifold S initial and S final, I guess. So then I think it's like you have to sum over all different ways that this initial thing can get mapped to this final thing, and this will depend on the topology. So if you sum over all of them, and that's how you choose to weigh different. I don't remember, man. Because it's supposed to take you from this to vector space, which is supposed to be like a Hilbert space. But sorry, this is some abstract categorical definition of a path integral that I don't remember how exactly is defined. I mean, you can see all these generalized symmetries people talking about. But okay, to be honest, I don't know what you gain from doing this. Like, if you can compute something that you couldn't before. I mean, there might be like mathematical reasons if you want to formalize different definitions of the path integral. And yeah, this is one that is very formal. I think like, yeah, Jacob Lurie and people work in this. Yeah, this is embarrassing. I forgot how this stuff is defined. But let's put the maybe low beat here, question mark. I mean, this is pretty good actually. Maybe here. Okay, some heavy hitters. Okay, so this is my experience, a good amount of my experience doing research in grad school. 24-year-old Kummer. So obviously Kummer, but like these are also a set of identities involving hypergeometric functions. 8-hour Gooning sessions in mathematica. So like just yeah, you can see me doing this kind of thing on my channel. Spent the last 2 years digging into increasingly depraved hypergeometric functions. So oh god. It turns out that there are quantities in my research that are of interest that you can express in terms of some of these functions, but the ones you need to use become increasingly general. So there's 2f1, there's the sort of original hypergeometric function that everyone knows and loves, a, B, C, D, or Z, I guess, and it's symmetric in these two arguments. It solves some second order differential equation. It's neuromorphic. It has a branch cut from z equals 1 to infinity. But yeah, so these functions are very nice. They have like a billion identities that you can use. But then they have various generalizations, PFQs where you have more arguments, Apple functions where you have, okay, so I guess you can express this 2f1 as a Taylor series, and these are Pockhammer symbols. So an is gamma of a plus n divided by gamma of a, and then c of n over n factorial. So you can you can write these as these kind of Taylor series. PFQs are, okay, what if I have more of these guys? I have, instead of 2 and 1, I have P and Q. Apple functions, or these horn functions, are what happens when I have it's a Taylor series in like more than one dimension, and these can also depend on n. And so Huen functions are even more complicated. I guess a lot of these can be, there's theory of GKZ, Galfand, Kapranov, Zelevinsky hypergeometric functions, and then they have these loci on which they diverge. They're amoeba, they're called. And it's like this very abstract kind of mathematical theory that people use with algebraic geometry, and I don't know very much about it. Doesn't know anything about these, just blindly applies identities hoping things will simplify. I mean, in the early days of doing this project, this was very much true. Ignorant of physical interpretation aside from holographic 2D waifus, this is talking about holography. Combinatorics knowledge reduces to this, so this is like something that is involved in manipulating 2f1s. What's a Mellon-Barnes integral? So MB integrals are, I guess there are different ways you can work with these hypergeometric functions. MB integrals are like integral expressions of them, but they're kind of unintuitive, and they're like hard to use, I guess. Looking for hidden symmetries, months chasing after love symmetry to prove its half-sided modular. I have a paper about this coming up. Runs in circles without picking up monodromy. It's like using the same, trying to use the same manipulations over and over. Homepages functions.wolfram.com. A bunch of these tabs open as you're gooning, looking for identities. Private browsing. I mean, yeah, I think this just captures a lot of frustrations associated with the grad school experience. I've been told that this is, I don't know about common, but other people have empathized at great length about this. So this is easily an S tier meme. I'm gonna put it over here. Okay, and finally we have this iceberg meme about spinners that I could spend like 2 hours just talking about. But let's keep it short because it's already 2, and I got things to do, like a meeting tomorrow and whatnot. But so the caption, I think I made this in the shattered aftermath of, like hours of nLab doom scrolling to come to the realization that no, I did not know what spinners are, and after that I spent like a good amount of time trying to understand some of the lower tiers, and I think I did, but now I don't think, at least this I can't recall. So it's like, what's a spinner, right? So that's like the kind of iceberg that you meet in like starting maybe from high school and undergrad physics to like grad school physics to like research. So the first thing you learn, it's like, oh right, it's like a ball that kind of like spins. It has some discrete angular momentum, intrinsic angular momentum as opposed to orbital angular momentum, which is what happens when like a planet, say, orbits around something else. And there are these Stern-Gerlach experiments where people discovered that spin was quantized. Pauli exclusion principle, where two particles can't occupy the same, two fermions, which are spin half integer, can't occupy the same quantum state. And sort of this is the pop science introductory level. And in your undergrad, you learn how like what Pauli spinners are. These are these 2-component spinners that transform under the rotation group. And you learn, so one of the ways to represent this the rotation group is through Pauli matrices, and then you can learn how to combine. So this would be SU2, which is the double cover of the rotation group. I guess this is the spin group of SO3, spin 3 rather, and so like there are Klebsch-Gordon coefficients, these Wigner J symbols that tell you how to take tensor products of spins. So for instance, if I have a spin 1/2 particle and a spin 3/2 particle, then if I put them together, what are all the different spins I can get? And then you take a QFT course where you learn the important group is SO1, 3. So this is the group of Lorentz transformations, and they act on fields like this, using, here's the metric, and the double cover of this is SO2, C. Spinners live in representations of this, and that leads you to like the Dirac equation. It leads you to gamma matrices, which are, they pop up in these representations. You can have different kinds of spinners. You can have Weil spinners, Dirac spinners, Majorana spinners. So Weil spinners are 2-component complex spinners. Dirac spinners are you basically taking 2 Weil spinners together. Majorana spinners, this is like it's like kind of also taking two Weyl spinors, but they're conjugates of each other, and so they have different properties. If you want to study spinors using the Euclidean path integral, you have to bring up these Grassmann numbers, which are numbers that square to 0. Okay, and then you can do this more generally, not SO3, but like in higher dimensions. And so you learn about Lie theory. You start with spin p comma q. This lead you to spinors in p plus q dimensions. How spinors live in projective representations of whatever your symmetry group is. Projective representations because in quantum mechanics you don't care about a phase, so they can be true representations up to some phase that need not be 1. So spin n is the covering space of SON, I guess, and basically doing this for in higher dimensions or for different kinds of groups. And then, you know, some of the, like, you learn about math, a lot of the heavy lifting math comes up, and this is how you define spinors at like a point, basically, using Clifford algebras over some vector space. And then there are these theorems that relate kind of representations of the Clifford algebra to representations of like your space-time symmetry group, the Cartan-Dion theorem. I think Wedderburn-Arden theorem is another theorem that has to do with representations of the Clifford algebra. I don't quite remember. When you're working with Clifford algebras, this is when you realize that this is actually the better signature. And yeah, there's this you notice this when you're looking for representations of Clifford algebras, it turns out that stuff is unique up to dimension mod 8, or like p minus q mod 8. So the types of spinors that exist are there are only a finite number of them, I guess, and so you can classify all of them. There's the spinorial checkerboard that you can write down. Jose Figueroa or Farrell has some great notes about these. So this is if you want to define properly spinors at a point. And if you have some manifold and you want to relate spinors at one point to spinors at another point. So in flat space, this is kind of trivial, but let's say you're in curved space, then this is not as trivial. You need a spin connection. You need to talk about the notion of frame bundles and principal bundles. So at every point on the manifold, you have some spinor structure, some kind of principal G bundle, and as you go from one to the other, that's what the spin connection allows you to do. To make sure that this is consistent, you need something like, you can define spinors on the entire manifold. You need something called the second Stiefel-Whitney class to vanish. Otherwise, you lack consistency. This is kind of like it's kind of like making sure your manifold is orientable. So, for instance, the Mobius strip is not. This is kind of like a higher version of that when you're talking about spin structures. You have D. This is the object that shows up in the Dirac equation in curved space. It tells you how, I guess, a spinor changes as it goes from one point to another in some way that respects symmetries. And then yeah, you can so there's like spin structure that you can talk about, but then you can, so I guess what happens, so for instance you have SO1 comma 3. This thing has some properties that you can talk about. For instance, you can ask how many disconnected components there are, and then this is like, this thing has 4 disconnected components, I guess. So this is like Z4 or whatever. Then you can ask what the first fundamental group is. The first fundamental group is how many loops there are that cannot be deformed into each other, I guess. So there are two classes of loops that, I don't know what you would call this, but there is like four discrete, I think, this would be like Z2 cross Z2. That's why people talk about the proper orthogonal Lorentz group, which is one of these. But then you can talk about how many loops are there that you cannot deform from one to the other, and basically, so if you only keep the connected part of the Lorentz group, then you get the special orthogonal group. So basically this kills pi 0. The set of disconnected components of this group is now trivial, and so you can do the same. You can consider the double cover of SO1 comma 3. This is spin 1 comma 3, and if you consider the double cover, this makes the first homotopy group trivial. So basically, if you consider this space, then there are no two loops that you cannot deform into another due to some topological obstructions. And so representations of this are called like spinors and such. Not all representations of spin 1 comma 3 are representations of SO1 comma 3. The ones that have integer spin. So that's kind of what you're doing here, but you can also consider, I think the second fundamental group is always trivial, but then the third fundamental group, I don't remember what it is. I think it might also be Z2, although this would probably be wrong. And then you can consider a cover of this that kills the third homotopy group, and this would give you string 1 comma 3. And you can consider representations of this. This would give you like string structures, and then you can consider higher homotopy classes. You get stuff like higher spin structures, like a 5-brane structure, and this entire thing is related to what's called a Whitehead tower. So you get these higher analogs of spinors and such, which I don't remember how to do anymore. These generalized symmetries people's care, like, you can read about this on the nLab. There are cool diagrams that are cool tables. If I go to like this higher spin structure, yeah, you can find these. Right, so you start with orientation structure, and then you want to add spin structure, some string structure, and you go higher and higher. And at points there are different obstructions that might obstruct you from defining these structures. So for instance here, this is just like if the manifold is not orientable, then you're out of luck. But then at this point there's something called a second Stiefel-Whitney class that you need to define spinors on your manifold, and so you can go higher and higher and higher. So the one I explained was the string group, and you need yeah, so okay, I mean, this is borderline incomprehensible. It's the reason why for that nLab post. But yeah, so the kind of the kind of iceberg for spinors, it goes very deep. I mean, I think like if people say they understand like this bottom of the iceberg, I think that's like really what a you understand like what spinors are, I think, very well. This is just I don't know, man. We'll see over the next few decades what new physics this gives us. But yeah, I made this in the shattered aftermath of nLab posting, nLab doom scrolling to realize that I don't know what spinors are. This is an S tier meme. Okay, so that I guess wraps this up. I don't know if you're still here. This is a very long video. I guess it might be nice to make some videos about, yeah, classification of spinors or effective field theory, because I have notes. I have recitation notes for all this stuff that people might want. I don't know, but yeah, thanks for watching, I guess, and yeah, have a great rest of your day.